Hardware engineering ultimately comes down to a physical medium. We're etching logic into literal silicon wafers, which means every algorithm we design has hard physical constraints. Take a standard sequence detector. Traditionally, engineers build these using a fixed pattern shift register. The hardware stores the last few incoming bits and checks against a hard-coded string, looking to detect exactly 1011 or another static pattern. But the real world does not always deliver neat, fixed strings. Often, hardware must parse dynamic, context-free sequences, like the mathematical model known as a to the n, b to the n. That notation represents an unknown variable number of consecutive A inputs, followed immediately by the exact same variable number of B inputs. That could mean 3 A's and 3 B's, or 10,000 of each. A standard shift register architecture breaks the moment that sequence length n changes unpredictably. If a register is physically built to hold 4 bits, it simply cannot buffer a 10-bit sequence to verify it. Attempting to solve this with a standard finite state machine means hitting a hard mathematical wall. To count an unbounded variable n using only static state transitions, the state machine would theoretically require an infinite number of hardware states. You cannot print infinite states onto a finite die. Solving dynamic sequence detection requires engineers to abandon static pattern matching and invent a new hybrid architecture. We solve this using a counter-finite automaton, or CFA. This architecture offloads the burden of sequence tracking from the state machine entirely, handing it over to a dedicated mathematical block. This diagram illustrates the CFA layout. It separates the hardware design into 2 distinct hardware modules, the FSM control logic and an n-bit data path counter. The data path counter handles the physical math. It increments its internal value for every A received in the data stream and decrements that value for every B received. Meanwhile, the FSM no longer tracks the sequence length itself. Instead, it issues increment and decrement commands and monitors a single 0 flag sent back from the data path counter. When the counter hits 0, the FSM verifies that the A's and B's match perfectly. By bridging a control state machine with a data path counter, we condense an infinite state problem into a highly efficient, finite, and physically producible hardware block. Moving this architecture from a schematic to actual silicon requires us to write behavioral Verilog. This relies on behavioral abstraction. Instead of manually mapping out the exact placement of logic gates and wires, we are scripting the algorithmic behavior of the module and trusting the compiler to interpret it. Within the FSM block, we define the internal state and next state variables using the reg data type. There is a common misconception here. Defining a variable as reg does not automatically guarantee it will synthesize into a physical hardware register. In Verilog, reg is simply a software data type used for storing values during simulation, much like an integer in C. Because the synthesis tool makes the final decisions on logic gates, behavioral modeling requires you to precisely format your code structure so the compiler correctly infers the exact hardware you intend to build. The most critical design rule for writing an FSM is strictly separating your next state logic from your actual state memory. This split-screen schematic shows how that next state logic is structured. We place it inside a combinational block, declared with the always at star syntax. This block acts as an instantaneous evaluator that recalculates the path the exact moment any input changes. Looking at the specific logic routing for state 3B001, the FSM queries the data path counter's 0 flag. This query creates a routing fork. If the 0 flag is active, the logic transitions to a success state. If it is inactive, the logic loops into a decrement state, continuing the process because the sequence is still resolving. Isolating this instantaneous decision-making within a dedicated combinational block prevents unpredictable race conditions during complex sequence evaluations. With the logic mapped, we shift focus to the sequential block, triggered by the always at pause edge clock syntax. This block governs the actual physical memory of the hardware. Its core action is simple. It transfers the newly evaluated next state into the active state register, executing this strictly on the rising edge of the system clock. To perform this safely, you must use the non-blocking assignment operator, written as a less than sign followed by an equal sign. This operates very differently from a standard blocking assignment, which executes sequentially line by line. The non-blocking operator ensures that all registers across the entire chip update concurrently at the exact same moment. Strict adherence to non-blocking assignments in your sequential blocks guarantees that your software simulation will exactly match the physical silicon behavior. Once the code is verified, the synthesis tool takes over. It analyzes our cleanly separated combinational and sequential Verilog blocks and begins routing physical paths. The software maps the sequential blocks into physical D flip-flops to hold state memory. Simultaneously, it weaves the combinational case statements into complex multiplexers for logic routing. This timing waveform chart shows the final validation of that hardware. When we feed an input stream of 3 A's followed by 3 B's, we see the counter value step up, then decrement perfectly back to 0, snapping the final validation signal high. The final CFA design requires a remarkably small physical footprint on the die, despite processing the variable complexity of context-free sequences. By translating mathematical constraints into properly decoupled RTL, engineers can bypass the limits of standard pattern matching. Mastering behavioral Verilog allows us to dictate the exact architecture of next-generation context-aware hardware.